Okay, good morning. Our third lecture is still about basic principle of fluids. So it is about fluid pressure, work energy, and power. So in this figure, you can see a hydraulic system. What you can see here, we have reservoir, and then we have the pump. The pump is connected with electric motor. And then we have pipings. And then we have check valves. We have directional control valves. We have hydraulic cylinder, and the hydraulic cylinder is connected to the external load. So here, mechanical energy entering the pump from electric motor. And then in the system, there will be heat energy out. And then hydraulic cylinder will move external load. So it means the mechanical energy out of the system. So hydraulic circuit is related to conservation of energy. The pump receives mechanical energy from electric motor. And then the pump receives low pressure fluids from the tank and delivers high pressure to the hydraulic cylinder. The hydraulic cylinder uses high pressure fluids to drive the external loads. And the hydraulic system delivers mechanical energy to an external load via hydraulic cylinder. The pressure reduces after delivering the load, and low pressure will return to tank. So the hydraulic system also transfer heat energy to surroundings that is created by frictional fluids flow through pipes, valves, and fittings. Okay, in flow, we can differentiate into laminar flow, turbulent flow, and then in transition flow. The flow will be laminar if the Reynolds number less than 2000, the velocity of the fluid is low, and then it is characterized by smooth straight line parallel to the pipe walls, and then each particle of the fluid orderly follows a smooth path, never interfere with one another. While turbulent flow, the Reynolds number is higher than 4000. The velocity of the fluids is higher. It is characterized by tiny whirlpool regions, and then each particle of the fluid flow chaotic and irregularly. Then we must remember what is Reynolds number. Reynolds number is dimensionless parameter that determine the nature of fluid flow. When discussing for internal flow, Reynolds number can be defined in the first equation. So RE equal to nu multiplied with D multiplied with rho over mu, or Reynolds number equal to nu multiplied with D multiplied with V. Okay, here Re is the Reynolds number, and then V is the velocity, and then D is the inner diameter of pipe, mu dynamic viscosity, and then no, this is no, yeah, is our kinematic viscosity. So all the unit you can see here, V in meter per second, D in meter, mu in Newton second per meter square, and then no is in meter square per second. So if the Reynolds number between 2000 and 4000, then the flow in critical or transition zone. If the dynamic viscosity known in centipoise and inner diameter in millimeter, so we can use this equation. So 1000 here is converting constant. If we use Reynolds number dimensionless, velocity in meter per second, diameter in millimeters, and then mu in centipoise. If the kinematic viscosity known in centistoke and inner diameter in millimeter, so we can use this equation. Re equal to 1000 multiplied with V multiplied with diameter over no. So here V in meter per second, D in millimeter, and no in centistoke. As the note, 1 millimeter square per second equal to 1 centistoke. So it means 1 meter square per second equal to 10 power 6 centistoke. Then again, when we studied fluid mechanics, we know exactly Bernoulli's equation. So Bernoulli equation is a derivation of conservation of energy equation. So if we have this configuration of pipe, then we can make the certain volume in volume control. So suppose the volume control has the has the width W1 and then has the velocity V1, and then having the pressure P1 at the elevation Z1. And then that volume control entering the system and then flowing here, and then at station 2, at the position of station 2, it has the width W2, and then the velocity V2, the pressure P2, while the elevation is Z2. From station 2, then the fluid flowing out. So in this case, there are several types of energy. The first is potential energy, pressure energy, and then kinetic energy. Potential energy is due to the elevation. At station 1, the potential energy is the width multiplied with Z1. At station 2, potential energy is the width multiplied with Z2. At station 1, the pressure energy is the width multiplied with the pressure P1 divided by gamma. While in station 2, that is the width multiplied with the pressure at station 2 divided by gamma. The last, the kinetic energy. The kinetic energy in station 1 is the width multiplied the square of velocity and then divided by 2g. While at station 2, the kinetic energy is the width multiplied with v2. So the square of velocity stay at the second station divided by 2g. So in this case, it makes commonly, but actually the width at station 1 for the same volume control in station 2 will have W2 and W1 equal to W2. So Bernoulli equation then can be expressed as the energy, total energy in the station 1 equal to the total energy at station 2. So the total energy consists of energy to the position, energy to due to the pressure, and then energy due to the velocity. So this equation can be simplified in this equation. So Bernoulli equation can be simply written as Z1 and then plus P1 over gamma and then plus V1 squared over 2g, that is equal to Z2 plus P2 over gamma plus the square of V2 over 2g. So in this case, Z is the elevation head. P over gamma is the pressure head. And then V squared over 2g is the velocity head. If the first equation, the units in joule, but here the second expression is in meter. And then we talk about losses in hydraulic system. Energy equation actually is the modification of Bernoulli. The total energy possessed by 1 pound chunk of the fluid at station 1 plus the energy added to it by pump minus the energy removed from it by the hydraulic motor minus the energy losses due to the friction is equal to the total energy possessed by 1 pound chunk of fluid when arrived at station 2. So it can be expressed in this equation where Hp in this case is the head of pump energy given to the system, and then minus and then Hm is the motor head, that is the losses due to the existence of which remove energy from fluid, and then Hl is the head loss. This is due to the friction losses. So it means the friction losses between station 1 and station 2. Remember this equation. This is energy equation for the hydraulic system. So head losses from joule to pump can be calculated using this equation, where the pump is in watt, and then the Q is in meter cube per second, and then gamma is in Newton per meter square. So in imperial system, we can use this equation. So Hp equal to 3950 multiplied with P over Q multiplied with specific gravity of oil, for example. Here, P is using the imperial system, so it means horsepower, and then Q is using the gallon per minute. And then we see HL. This is the losses in hydraulic system due to the friction. Friction is considered as main cause of high energy losses in hydraulic conductor. Using Darcy equation, we can calculate the head loss due to friction in pipes for both laminar and turbulent flow. So the expression is HL equal to F multiplied with L over D multiplied with the square of V over 2G. Here, L is the head losses in pipe, and then F is the friction factor. It depends to flow in laminar or turbulent, and F is dimensionless. And then L is the length of the pipe. It can be in meter or feet. And then D is the inside diameter of the pipe, so the dimension in meter or feet. And then V is the average fluid velocity, so in meter per second or feet per second, while G is the acceleration of the gravity. Usually we use 9.81 meter per second square or 32.2 feet per second square. And then F, friction factor for laminar flow, simply approximated using this equation. So 64 over Reynolds number. If we use this friction factor for laminar flow, so it means HL equal to 64 over Reynolds number, and then multiplied with L over D, and then multiplied with the square of V over 2G. So the above equations also called Hagen-Poiseuille equation, which valid for laminar flow only. And then we see the losses in hydraulic system. That is frictional losses in turbulent flow. We have the frictional factor for turbulent flow. Modi diagram and pipe relative roughness is commonly used to determine friction factor for turbulent flow. And then the friction factor can be found after Reynolds number and pipe relative roughness already calculated. The pipe inner surface depends on the pipe materials. So we need to define the pipe relative roughness. that is pipe inner surface roughness divided by pipe inside diameter, or epsilon over D. In this table, we can see the frictional factor for turbulent flow. So, for example, glass or plastic, it is very smooth. So the epsilon usually take to be 0. And then drawn tubing, the epsilon value equal to 0.0015 in millimeters or 0.0006 in inch. And then, for example, galvanized iron in millimeter 0.15 and then in inch 0.009. Riveted steel in millimeter epsilon equal to 1.5 and then in inch epsilon equal to 0.072. So here from the upper position to the lower position, the roughness surface is increasing. Glass or plastic very smooth, and then draw tubing smooth, commercial steel or wrought iron more rough, and then this is the roughest surface materials, riveted steel. So this is Moody diagram. To determine previously, to determine the friction factor, but for turbulent flow. So in Moody diagram, the horizontal axis is the Reynolds number, and then the vertical axis is the friction factor F. How to determine the friction factor for certain Reynolds number? First, we must determine the relative roughness, epsilon over D. So if we see epsilon using this table, and then we see the inner diameter of the pipe, so we can have certain value. So for example, relative roughness is, for example, 0.02. And then we have the line. So that is the friction, friction factor F for for a relative roughness 0.02. Following this line, and then if the fluid, the fluid inside pipe having a Reynolds number, for example, 10 power 5. So 10.5 Reynolds number has the line here. So it means if the relative roughness 0.02 and Reynolds number 10 power 5. So we can follow here this line, this line, and then here. Here is 10 power 5 Reynolds number. So it means we have this point and then we read to this part. So this is about 0.0195. So that is to determine the F value for certain value of relative roughness and certain value of Reynolds number. And then there is also losses due to valves and fitting. They are defined as HL equal to K multiplied with V squared over 2G. Here HL is the head losses in valves and fitting, and then K is the loss coefficient of valve or fitting. So the K depends on the type of valve or fitting. It is given in this table. For example, if we have the Klug valve and then a half open, the K factor will be 12.5. And then if we have the standard elbow pipe, standard elbow connecting pipe, so the K factor will become 0.9. Then the losses in pipe also depending on the length of the pipe. So there is a technique that is called equivalent length technique. So in this technique, the convenience approach of examining valve and fitting were a pipe with length L. So this technique is used to find length of pipe that would produce same head loss as a valve or fitting at the same flow rate. So HL halo lagi ngajar. Ini karena agama lagi juga. Karena agama. Iya. Apa tablik akbar. Ya udah dulu Bapak lagi ngajar ya. So, okay, head loss due to valve or fitting is made to be equivalent with the head loss in pipe, in straight pipe, in certain equivalent length. So, due to valve and fitting, we have K V square over 2G. And then for the straight pipe, we have F L, the length over T, and then multiplied with the square V over 2G. The length here is is given the subscript E. So it means this is becoming equivalent lengths. Then this equation can be simply written to find the equivalent length. So the equivalent length become K multiplied with D over V. So this is called by equivalent length technique. Okay, then here is the basic hydraulic analysis example. We are given the system. Find pressure available at the inlet in the hydraulic motor, so at station 2, for the hydraulic system in the figure to the right if the pump is adding 3 kilowatt to flow 0.00178 meter cube per second of hydraulic oil. The pipe has 25.4 millimeter inside diameter. The specific gravity of oil is 0.9 and kinematic viscosity of the oil is 75 centistoke. So we see the system. Then we make the reference. So the first reference is the oil level inside the tank. And then second reference is the oil position when entering the hydraulic motor. So we can refer first position. So this is flowing here and then passing the pump and then until this point. So in general, we refer to first position to second position. We write the energy equation. So this is the energy equation such as shown in previous page. This is still general, so we include about the additional energy of the pump and then the reduction energy due to the motor and then the reduction energy due to the losses in pipe and fitting or valve. Okay, so the strategy to solve is we see first at the position 1. So the position 1. So we imagine position 1 and then there is a streamline entering here and then going here. So position 1 is the oil in the tank. The number of oil in the tank is very much. So due to the flow, the decrement of the surface here is neglected. So it is assumed that at velocity 1, the velocity is 0. So the decrement of the decrement rate of the surface is 0. So it means the value of V1 square over 2G is 0. And then if we see position 2, of course, the fluid have certain velocity. And then if it is mentioned that the flow rate is 0.0017 meter per second square, And then we are given the diameter, inner diameter of the pipe 25.4 millimeter. Of course, from these given parameters, we can calculate what is the velocity of the oil in station 2 here. So we have V2 equal to the volume flow rate divided by the area of the pipe. So we can calculate. Of course, the units is expressed in meter per second. After knowing V2, then we can calculate this value, V2 square over 2G. So V2 square over 2G, we can calculate. The unit is in meter because this is equation in head. After that, we need to calculate SL. So the losses due to the pipe or fitting. So first we must investigate, is the flow here laminar or turbulent? Okay, then we calculate the Reynolds number first. Based on the calculated velocity in station 2, so we can calculate the Reynolds number. Okay, so the Reynolds number here is calculated 1000 multiplied with velocity multiplied with the inner diameter divided by nu. So if you calculate the Reynolds number, the value of Reynolds number, you will find the value of Reynolds number below 2000. So it is laminar flow. Since the laminar flow, so the friction factor easily calculated using this approximation equation. 64 over the Reynolds number. So you can calculate the friction factor. Okay, that is the friction factor F. Then, considering loss due to the elbow and fitting. So if we see here, flowing here and then going here. So we find only one elbow. And the elbow is standard elbow with inner diameter 25.4 millimeter. So it means we have only one elbow. Then we convert the elbow, the loss in elbow to the equivalent loss if the elbow is assumed as the straight pipe. So it means the equivalent length for elbow, that is equal to K multiplied with D over F. And then we see the materials. The pipe, okay. We see the elbow. Elbow is the standard elbow. So we see here, what is standard LPO? Standard LPO is 0.9. So it means this is becoming 0.9 and then multiplied with the diameter. Diameter is 0.0254. So this is taken to meter units and then divided by the F. The F is calculated here. So if you calculate it, so you will find this result. So 0.425. Then we calculate the total length, total equivalent length. So it means the total length of all pipes plus the equivalent length for the LPO. If we see the system, so we have this pipe. So this pipe, the first is we have the first pipe, second straight pipe, and then third straight pipe. So it means we have that is pipe 1 plus pipe 2 plus pipe 3 plus L2. Then you can calculate. We will find that the equivalent total length of pipe equal to 6.83. So here we can see, you can see this is pipe 1, pipe 2, pipe 3. Pipe 1, it is mentioned the length is 0.305 meters. And then pipe 2 and pipe 1 and pipe 3 is not mentioned, but we see here the elevation is 6.096 meters. So it means here pipe 1 plus pipe 3 equal to 6.096 meter. Okay, then after finding the equivalent total length, so the head loss of conductor, so it means conductor means pipe fitting, and pipe fitting, elbow, and so on. So we have SL and then F multiplied LE over D and then multiplied with V squared over 2G. We use LE, this value, the total equivalent length of pipe. So we can calculate. So until now, if we see this this value, so we have calculated SL. And then we have calculated head energy due to kinetic energy to velocity. Yeah. Okay, now we will calculate SP. So the pump. The pump is mentioned 3 kilowatt. Okay, so it means now the head pump, we have this equation. SP equal to P over Q times gamma. So we can calculate first. Gamma oil is specific gravity of oil multiplied with gamma water. So it means 0.9 and then multiplied with 9,807 Newton per meter square. So this is the result of 1,000 multiplied with 9.807 as the gravity acceleration. So we will have the gamma oil 8,826 Newton per meter square. So it means we can calculate. This is given 3 kilowatt. This is given also, and then this has been calculated here. So HP 0. Okay, then see again the fluid flow from point 1, position 1, following this pipe, following this elbow, following this pump, and then until post 2. So we can see here, along this flow, there is no motor, no hydraulic motor. We have only pump here. So it means hydraulic motor here is 0. See, although this is electric motor, but this is outside. This is outside the hydraulic system. Electric motor is only giving the energy to the pump. So the hydraulic motor we assume right here is the hydraulic motor that is supporting the load, that is giving the power to the load. So it means Sm, this is equal to 0. So motor head Sm equal to 0. There is no hydraulic motor between station 1 and 2. Okay, then finally we can rewrite again the basic equation, and then this is 0, this has been calculated, this has been calculated, this has been calculated here, this has been calculated, and the value is 0. And then Z1 and Z2 also known. So the time that is not that has not been calculated yet is this P2. So taking P1, if P1 is exposed to atmosphere, this is the level, this is the fan. So the post 1, the surface of the oil is exposed to the atmosphere using the fan here. So this is not pressurized air. It is just the atmosphere air. So it means P1 known, 1 atmosphere. So finally we can enter the P1 here, and then the remaining unknown term is only P2 over gamma. Then we can calculate the pressure at the station P2. So we will have 1.54 megapascal. Okay, that is the simple basic hydraulic analysis example. Okay, then about hydraulic conductor sizing. The steps in determine fluid power, conductor size or pipe size. The first, calculate the minimum acceptable inside diameter based on the flow rate required. Second, select standard conductor with inside diameter equal or greater to result obtained from step 1. So see what is flow rate required, and then what is acceptable diameter. Then select the pipe with inside diameter equal to 1 or greater that is available in the market. And then determine the wall thickness based on the standard size. Based on the conductor, material, and system operating pressure, determine the tensile strength S and safety factor. And then calculate the burst pressure BP and working pressure WP. And then if the working pressure larger than the operating pressure, the conductor size is accepted. If the working pressure is less than the operating pressure, then different diameter and wall thickness of standard size must be selected. Okay, in flow requirement, a fluid power conductor must enough cross-sectional area to handle the flow rate required without producing excessive fluid average velocity. So we use this equation. The area equal to volume flow rate divided by the design or expected velocity. And then a fluid conductor must strong enough to prevent bursting due to excessive hook stress on the wall of the conductor. When we study solid mechanics, we have this relation. So the tensile stress, that is the normal stress, equal to the pressure inside the pipe and then multiplied with inner diameter divided by 2 thickness. So we can use this relation to calculate the pressure or to calculate the tensile stress in the pipe wall. And then when the stress, so it means normal stress, sigma, acting on the conductor is equal to conductor material tensile strength, the pipe will burst. So the burst pressure equal to 2 and then T and then S, the tensile strength of the material divided by DI. And then the working pressure. The working pressure equal to the burst pressure divided by the safety factor that we want to we want to be able at the pipe. So safety factor usually taken as 8 for the pressure 0 until 70 bars. and then taken as 6 for pressure 70 until 170 bars, and then safety factor about 4 for pressure above 170 bar. This is the example. A steel tube of IC 4130, which has the tensile strength 517 megapascal with 12 mm inner diameter and 15 mm outer diameter, is going to be used for pneumatic system. Determine working pressure of this tube if the safety factor is 6. Okay, first we see inner diameter 12, outer diameter 15. So the difference between inner diameter and outer diameter, of course, is 2 times of the thickness. So it means the thickness becoming 3 millimeters over 2. Then we use the burst pressure 2Ts over Di to multiplied with 1.5 and then multiplied with 517 megapascal divided by Di 12 millimeters. Remember again, when you studied solid mechanics. When we studied solid mechanics, if we use the force in Newton, and then all length dimension in millimeter, so we will have the stress in megapascal. So simply just use T in millimeter, S in megapascal, and then D in millimeter. And then the working pressure, the WP, okay, working pressure. Okay, the working pressure is including the safety factor. So the working pressure is the burst pressure divided by SF. And then if we want to make the safety factor 6, so it means this value divided by 6. So we have 21.57. Okay, so that is our lectures. Repeating the basic principles of fluid by accompanying the example of simple hydraulic system. Okay, thank you, my students.